Problem set number 4, question number 11. Here we are asked to compare an observation, a single earthquake magnitude of 7.8, to a long-term population kind of mean of 3.5. This is a little weird in that we're given what is effectively a population mean that normally, when given a population mean, we compare it to a sample mean, and this is a distribution of sample means. But in this question, that is not the case. We have a long-term mean that still goes in the middle, but we are comparing it to an observation, a single earthquake that has a magnitude of 7.8. Because we are dealing with an observation and asking for a probability based on an observation, this distribution needs to be of observations. So a distribution of observations gives us an associated distance in standard deviations. Remember, observations and deviations go together. So it doesn't really matter that this mean is a population mean versus a sample mean. What matters is that this will be a distribution of observations, and so we have to use standard deviations. In order to do that, we have our data point over here. This is 7.8 earthquake units, magnitude units, whatever that ends up being. That is our original data units. In order to do probability calculations with the normal curve, we need to convert those original data units into standard deviation units. And we do that by calculating the z-score. So the z-score for this question I have laid out here. We take the observation, 7.8, subtract that from the mean, 3.5, and again, it doesn't matter that it's a sample mean or a population mean, just as long as it is the mean, or the value we want to compare it to. And then we divide by the standard deviation. That 2, the standard deviation, was given to us directly in the problem. It's not something we had to calculate. So when we do the math here, we get a z-score of 2.15, positive 2.15. So that tells us that the observation, 7.8, is about 2 standard deviations away from the mean, 3.5. We can then ask the question, well, how likely is it to be 2.15 standard deviations away? So what is the area under the curve here? So this kind of critical region. That's just a simple question. I'll put simple in quotes there. Simple question about probability. And so we will invoke the Excel function for normal distributions where when we know the distance, so we've calculated that is our z-score, and we want the probability. So the norm.s.dist, remember the s is for a generic normal curve when we don't have information about the mean, the standard deviation, the standard error. We actually do have that information in this case, but we don't need it. What we need is just the distance. So we can plug this in, the normal distribution. It is a standardized one where all we care about is the distance away. We have to give it the distance, and remember that is the distance of our data. Notice here we don't have anything about critical values. This isn't the kind of hypothesis testing that we've been doing. So we just give it the distance of our observation in standard deviation units. So 2.15, it's the z-score up here. True means that, at least for this part of the function, we are calculating the probability from negative infinity up to that value. That is the way Excel does these kind of calculations, always starting from negative infinity, moving off to the right. Well, that's great, and it gives us a number, but we want the part that is to the right of 7.8. And Excel gave us the part to the left, so the whole area of the curve is equal to 1. So let's take, now that I've hidden it, let's take 1 minus what Excel actually gave us, and the result will be this part over here, which is what we actually want. So that tells us the probability, the area under the curve that is at least 7.8 or greater, is 0.015, so about 2%.